We'll start in 1 minute. Today we'll be in section 5.2 on properties of exponents. And a reminder, the quiz 4 was emailed this morning and it's due tonight by midnight. And also there is no school on Monday. Okay, chapter 5, section 2, properties of exponents. So here's a definition. If b does not equal 0, and if n is a positive integer, then b raised to the power n can be written this way. We refer to the number b as the base of the term, b to the power n, and the exponent is n. When n is a positive integer, and then as a reminder, the positive integers are the counting numbers, 1, 2, 3, 4, and so on, then b raised to the power n is shorthand for b times b times b, and so on, where b is a factor n times. Okay, so to illustrate that, 2 raised to the power 4 well, what does that mean? It means 2 times 2 times 2 times 2. And then when you multiply 2 times 2 times 2 times 2, you get 16. But even though the exponent 4 is not very big as far as the size of the number, you might agree that writing 2 to the 4th is more efficient than writing 2 times 2 times 2 times 2. 3 to the 2nd, that means 3 times 3. The factor 3 appears twice, and then that simplifies to 9. 5 to the 3rd, 5 times 5 times 5. 5 times 5 is 25, and 25 times 5 is 125. Okay, then 7 to the 10th. 7 to the 10th means 7 times 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 7. I'm not going to do that one, but this is what 7 to the 10th means. 7, the factor of 7 appears 10 times. And now let's look at some of the properties of exponents. Here we let a and b be non-zero real numbers, and we'll let m and n be integers. Okay, the product rule for exponents, if you multiply a to the m times a to the n, you can simplify that to a to the m plus n. So if the base, here the base is a in both terms. If you're multiplying two terms that have the same base number, then you can write the base and add the exponents. Okay, here's an example. 2 to the third times 2 to the second. That means 2 to the 3 plus 2. We're adding the exponents. 3 plus 2 is 5, so this is 2 to the fifth. And 2 to the fifth, 2 times 2 times 2 times 2 times 2 is 32. So 2 to the fifth, that's one of the basic ones that you should know by heart. Okay, a quotient rule. Quotient implies division, so you have a numerator and a denominator. The quotient rule for exponents, if we divide a to the m by a to the n, then we can write that as a to the m minus n. In this example, 3 to the fourth divided by 3 to the third is 3 to the 4 minus 3. 4 minus 3 is 1, so we get 3 to the first, and then 3 to the first is just 3. Okay, we also have negative exponents. A raised to the negative n is equal to 1 divided by a to the positive n. Okay, in this example, 5 to the negative 2, well, that's equal to 1 over 5 to the positive 2. And 5 to the second is 25, so this simplifies to 1 over 25. And then we have the zero exponent. Okay, remember a is non-zero, so a non-zero number raised to the exponent 0 is equal to 1. So 7 raised to the power 0 equals 1. Okay, in our next little exercise, we'll prove the zero exponent property. And we'll use other properties to help us. Okay, so we'll let a be a non-zero number and let m be an integer, positive integer. Well, an integer. Okay, so if we divide a to the m by a to the m, a to the m divided by a to the m, if we divide a non-zero number by itself, we know that that's equal to 1, right? No disagreement about that? But then if we use the quotient rule on a to the m divided by a to the m, so a to the m divided by a to the m is equal to a to the m minus m. That's according to the quotient rule. But m minus m is 0. So this is a to the 0. Okay, so on one hand, a to the m divided by a to the m equals 1. And on the other hand, a to the m divided by a to the m equals a to the 0. Therefore, we can say a to the 0 equals 1. So ergo, a to the 0 equals 1. Okay, let's do one more thing before moving on to the next page. So this will involve the negative exponent. So a to the negative n well, we already have a property that says that that's equal to 1 over a to the n. But I want to illustrate a way to verify that that's the case by using the other properties. The exponent negative n, so perhaps you'll agree that that's equal to, the exponent is equal to 0 minus n. 0 minus n and negative n are equal. And then if we use the quotient rule in reverse, so up here, using it in reverse, we would say a to the m minus n is equal to a to the m over a to the n. So if we do that here, we get a to the 0 divided by a to the n. But we just proved that a to the 0 is 1, so this is equal to 1 over a to the positive n. Okay, so that might help you remember this negative exponent property. Okay, let's move on to the next page. More properties of exponents. Let a and b be non-zero real numbers, and let m and n be integers. Okay, here we have a power property. Inside the parentheses, we have a to the exponent m, a to the power m, and then we're raising that quantity to the power n. So a to the m to the n. We can simplify that by multiplying the exponents, m times n. If we apply that property on this one, 2 to the third to the second is 2 to the 3 times 2. 3 times 2 is 6, so this is 2 to the 6th. And 2 to the 6th, that's 2 times 2 times 2 times 2 times 2 times 2. This turns out to be 64. Okay, to verify this rule in this example, another way to interpret 2 to the third to the second since the outer exponent is 2, this is 2 to the third times 2 to the third. And then a property that we saw on the previous page, 2 to the third times 2 to the third is 2 to the 3 plus 3, or 2 to the 6th. So in this case, there are two ways to come up with 64. One is just to use the power property, or the other one, use the other property that we called the product rule. All right, the next property. This time we have a times b that is raised to the power m. So a times b is in parentheses. And this is equal to a to the m times b to the m. Applying that in this property, or in this example, 2 times 5 to the third, that's 2 to the third times 5 to the third. And we should simplify these fairly small numbers. 2 to the third is 8. 2 times 2 times 2 is 8. 5 to the third, 5 times 5 times 5 is 125. And 8 times 125 is 1,000. Hey, this is probably the most efficient. Well, maybe not the most efficient, but this is just illustrating this property. Another way, well, we can easily evaluate 2 times 5. So this just becomes 10 to the third, which is 10 times 10 times 10, which is 1,000. Okay, moving on. The next property, quotient to a power. That's like saying you're going to raise a fraction to an exponent or to a power. So here we have a rational expression or a fraction, a over b, raised to the power m. Since the exponent m is on the outside of the parentheses, it means that the exponent can be applied to the numerator and the denominator. So a over b in parentheses to the m is a to the m over b to the m. In this example, 3 over 5 to the fourth, this is 3 to the fourth over 5 to the fourth. And 3 to the fourth, 3 times 3 is 9, times 3 is 27, times 3 is 81. So 3 to the fourth is 81. 5 to the fourth is 625. Hey, here's another negative exponent. So the one on the previous page had a to the negative n equals 1 over a to the positive n. And this time we have 1 over a to the negative n equals a to the positive n. Hey, one way to prove that, if we begin with 1 over a to the negative n, since the numerator is 1, we can replace that with a to the 0. So we have a to the 0 over a to the negative n. And then we can apply the quotient property. A to the 0 divided by a to the negative n is a to the 0 minus negative n. But 0 minus negative n is 0 plus n. So that's just equal to a to the n. So that's what this property says. Another way to think about this before we do this other stuff. If you have some number raised to a negative exponent in the numerator, and some number raised to a negative exponent in the denominator, then this is what you can do. 2 to the negative 3 in the numerator is equivalent to 2 to the positive 3 in the denominator. 3 to the negative 4 in the denominator is equivalent to 3 to the positive 4 in the numerator. And then this factor of 5, that's like 5 to the first power. That just stays where it is. And then you can evaluate further. 3 to the 4th is 81. So in the numerator is 81 times 5. In the denominator, 2 to the 3rd is 8. So this can be written as 405 divided by 8. Okay, but another property involving a negative exponent, if you have a over b in parentheses with a negative n for an exponent, then you can write the reciprocal of a over b, which is b over a, and change the exponent to positive n. And then b over a in parentheses to the power n can be written as b to the n over a to the n. Okay, this example, 1 over 7 to the negative 2. Well, that's just 7 to the positive 2. 7 times 7 is 49. In the next example, we have a fraction 5/4 to the negative 2. So if you have a fraction raised to a negative exponent, then write the reciprocal of the fraction. The reciprocal of 5/4 is 4/5. And then change the exponent to positive 2. And you can simplify this in a couple of ways. We can apply the quotient to a power property. So this is 4 to the 2nd over 5 to the 2nd, or 16 over 25. Or an alternative, 4/5 to the 2nd, that means 4/5 times 4/5. And then when we multiply fractions, we multiply the numerators. 4 times 4 is 16. Multiply the denominators. 5 times 5 is 25. And the way to get good at evaluating expressions with exponents is just to practice and review the properties. I wouldn't worry about memorizing the names of the properties. I don't really remember them that well myself, but I know how the properties work. And so if you practice and then read the properties, that will be very helpful. Okay, the next page. Simplify the following. Hey, there are some little things that you'll want to make sure that you get a handle on. So this one on the left, negative 3 to the second. This does not mean the same thing as the number negative 3 in parentheses to the second. So in this case, 2 applies to the number 3, but not to the negative. So one way to interpret this is negative 1 times 3 to the second. And if you remember the order of operations, we have to evaluate a term with an exponent before we evaluate multiplication. So 3 to the second is 9, and then negative 1 times 9 is negative 9. So this is the negative of 3 to the second. So it's the negative of 9. This term over here to the right means something different. Even though we might read them the same way, they don't mean the same thing. So this one on the left, we could read that as negative 3 to the second. When we read this one on the right, we say negative 3 to the second. They sound the same, but they don't mean the same thing. Since negative 3 is in parentheses and it's raised to the exponent 2, this time the exponent 2 applies to the base number negative 3. So this means negative 3 times negative 3, which is positive 9. Okay, so make sure you get a handle on this, on the difference between those two. In the next pair of examples, this one means the negative of 3 to the third. So you can interpret it as negative 1 times 3 to the third. You don't have to write it. Just remember that if there's not parentheses around the number negative 3, then we're going to evaluate 3 to the third first and then multiply it by negative 1. So 3 to the third is 27, and then negative 1 times 27 is negative 27. So the negative of 3 to the third is the negative of 27, or negative 27. Maybe the example on the right means something different. This time the number negative 3 is in parentheses. So the number negative 3 in parentheses to the third power this means negative 3 times negative 3 times negative 3. Negative 3 times negative 3 is 9. And then 9 times negative 3 is negative 27. Okay, so here is a pair of examples that both have the same number, the same outcome, negative 27, but they don't mean the same thing. So it's possible, in a case like this, it's possible to get the right answer for the wrong reason. But it will catch up to you eventually if you don't distinguish between the two interpretations. Okay, now we'll look at applying the properties with variables. So here we have x to the third times x to the fourth. Simplify that. So online you can type in, you can use the caret. If you hold down Shift and the number 6 key, that gives you the caret, which is a symbol that represents that you're raising something to an exponent. So what does x to the fourth times x to the, what does x to the third times x to the fourth simplify to? Okay, we got an answer online, x to the seventh. So an intermediate step is x to the 3 plus 4, which is x to the 7th. The next one, x to the 7th divided by x to the 2nd. So here we apply the quotient property, and we get x to the 7 minus 2, which is x to the positive 5. Okay, next we have a rational expression, y to the third divided by x to the fourth, that is raised, that entire rational expression or fraction is raised to the exponent negative 4. So when we're simplifying, in the end, we only want positive exponents. Okay, so we have y to the third over x to the fourth, all raised to the negative 4. Now, there's more than one way to go about it. Since the outer exponent is negative, we can write the reciprocal of the fraction. The reciprocal of y to the third over x to the fourth is x to the fourth over y to the third. And then change the outer exponent to positive 4. And then we can multiply the outer exponent 4 times each of those exponents. So in the numerator, x to the fourth is x to the 16th. And in the denominator, y to the third to the fourth is y to the 4 times 3, or y to the 12th. So this is the simplified answer. We cannot simplify any further because the variables are different. So this is as far as we can simplify it. An alternative, we can apply the outer exponent directly by multiplying -4 times the exponent 3 in the numerator. That gives us y to the -12th in the numerator. And in the denominator, we have x to the 4th to the -4, or x to the -16. So from here, if you remember what I said earlier, if you have a term with a negative exponent in the numerator, you can write the term in the denominator if you change the exponent to a positive. So we can, instead of y to the -12 in the numerator, we can have y to the +12 in the denominator. And similarly, if we have x to the -16 in the denominator, that's equivalent to x to the +16 in the numerator. Or you could take it one step further. You could write this as a product of terms, y to the -12 over 1 times 1 over x to the -16. So now it's just overkill. So I'll just go ahead and write the result. Y to the -12 over 1 is 1 over y to the +12. And 1 over x to the -16 is x to the +16 over 1. So we get the same result either way. And the next example. Here we have, in parentheses, x to the 2nd over 2, and that expression is raised to the exponent 2. So on this one, it's possible to get the correct answer for the wrong reason. So what does this simplify to? X to the 2nd over 2 raised to the exponent 2. Well, since the outer exponent is 2, we could just write this as x to the 2nd over 2 times x to the 2nd over 2. And then just multiply the fractions. X to the 2nd times x to the 2nd is x to the 2 plus 2. And in the denominator, 2 times 2. So we get x to the 4th divided by 4. Okay, the next example, in parentheses, we have 4 times x to the 3rd times y to the 2nd, and that entire term is raised to the exponent -4. Okay, so in the end, we want only positive exponents. All done? Well, there's a couple of things we can do. Since we have a number that's a factor, 4 is a factor, you can think of 4 as 4 to the first. So I'll rewrite this as 4 to the first times x to the third times y to the second raised to the outer exponent -4. So one of our properties applies here. If we multiply the exponent -4 times each of those exponents, we get 4 to the -4, because -4 times 1 is -4, times x to the -12 times y to the -8. In the end, we want only positive exponents. But this is like having a denominator of 1. When the denominator is 1, we don't usually write it, but since we have terms with negative exponents in the numerator, eventually we're going to have a denominator with something other than 1. Remember, 1 is a factor of everything, so a factor of 1 has to stay in the numerator no matter what, right? But 4 to the -4 in the numerator is equivalent to 4 to the +4 in the denominator. X to the -12 in the numerator is equivalent to x to the +12 in the denominator. And then finally, y to the -8 in the numerator is equivalent to y to the +8 in the denominator. And so the only thing left to do is evaluate the number 4 to the 4th. So 4 times 4 is 16, times 4 is 64, times 4 is 256. So in other words, 4 to the 4th is 256. So our simplified term is 1 divided by 256 times x to the 12th times y to the 8th. Hey, let's look at the next page. Okay, this first one, we are multiplying. We have 2 terms in parentheses, and it's understood that we're multiplying. Inside the parentheses on the left, we are also multiplying m times n to the -3. We're multiplying that by m to the -5 times n to the -2. So m, if you don't see an exponent, it's understood that the exponent is 1. So in the end, we want each variable to appear once only, and we want its exponent to be positive. So we can rearrange the terms since we're just multiplying. We can rearrange this so that we have m to the 1st times m to the -5 times n to the -3 times n to the -2. Then we can simplify m to the first times m to the negative 5 by adding the exponents. So we get m to the 1 plus negative 5. And then we have two factors with a base n, so we can write that as n to the negative 3 plus negative 2. Now we're just a couple of steps away. M to the 1 plus negative 5 is m to the negative 4. And n to the negative 3 plus negative 2 is n to the negative 5. So now we want to remind ourselves that the denominator is 1. And since both factors in the numerator have negative exponents, we also want to remind ourselves that 1 is a factor in the numerator. And then the last step, m to the negative 4 in the numerator is equivalent to m to the positive 4 in the denominator. And then the factor n to the negative 5 in the numerator is equivalent to n to the positive 5 in the denominator. So that is our simplified result. Okay, the next one is similar. This time we have a coefficient of negative 5 in this term on the left and a coefficient of 8 in the term on the right. So if we rearrange terms, we'll write negative 5 times positive 8 times a to the negative 2 times a to the 7th times b to the negative 8 times b to the 6th. Negative 5 times 8 is negative 40. A to the negative 2 times a to the 7th is a to the negative 2 plus 7, or a to the positive 5. And b to the negative 8 times b to the 6th is b to the negative 8 plus 6, or b to the negative 2. Okay, so now we're just one step away. One of the factors in the numerator has a negative exponent. So remind ourselves that we have a denominator of 1. So in the numerator, we still have negative 40 times a to the 5th. And then in the denominator, we have b to the positive 2. Okay, this factor, negative 40, remember to not treat, that's not a negative exponent. That's a negative number, but it's a negative factor, but it's not an exponent. So it stays in the numerator. In the previous step, we had b to the negative 2, so that's equivalent to b to the positive 2 in the denominator. Okay, we can get started on the next one. Okay, this time we have a rational expression raised to a negative exponent. So there's more than one way to do it, but notice that we can simplify inside the parentheses. So let's do that first. We have a factor of 4 in the numerator and 7 in the denominator. And then if we focus on j to the 7th divided by j to the 3rd, that's equivalent to j to the positive 4 in the numerator. And then k to the 4th divided by k to the 9th, that's equivalent to k to the positive 5 in the denominator. Now, since the outer exponent is -2, what we do is we write the reciprocal of the fraction. So in the numerator, we'll have 7k to the 5th. In the denominator, 4j to the 4th. And we change the outer exponent to 2. And then think of 7 as 7 to the 1st, and think of 4 as 4 to the 1st. So now we can apply the outer exponent 2. So in the numerator, we're going to get 7 to the 1 times 2. 7 to the 2nd is 49. 7 times 7 is 49. Times k to the 2 times 5, or k to the 10th in the numerator. And in the denominator, we have 4 to the 2nd, which is 16. And then j to the 4th to the 2nd is j to the 8th, because 2 times 4 is 8. Okay, we're out of time, so go ahead and sign in for attendance.
Happy weekend.